So just a short screencast today. I've got some slides which might actually be more fun to look at than the text we got. So this is just a quick summary of some points of C++ and programming in C++ using CoCoALib. I'll just skip through this fairly quickly. I think it's more important to spend time actually doing things rather than listening to presentations. So first thing, quick recap of the C++ language. It's actually sort of shifting sands in a sense. It's a language that's evolving over these years. So the first real version, the first fully standardized version was C++ 03, then became 11, 14, 17, 20. They're already talking about C++ 23, and no doubt future versions are planned. We should be mostly concerned with a subset of C++ 14. That's the version of C++ that we're using in CoCoALib, and there are actually problems going into the future. They've introduced a change which is not backward compatible, and that's causing some trouble with CoCoALib. We don't yet know how to fix that. So C++ 14 is essentially the one that we're wanting to look at here. So C++ itself is a relatively small programming language, which I'll summarize in just a moment, and a relatively large standard library or standard template library. So here's a quick summary of the language, some of its features and its syntax of perhaps the main functions. This is not complete. There are a number of things that are not here. So one important point compared to CoCoA5 is that we have to have fairly explicit static typing for variables and function return values. That means every time we introduce a variable in C++, we have to say exactly what type of value it will hold. Similarly, when we declare a function, we have to say what type of value that function returns. We didn't need to do that in CoCoA5. This extra discipline on the whole is good. It helps lead us towards good design and reliable programming. But it can be a bit annoying when you first encounter it. C++ itself has very few basic types. It has booleans. So I've written int here, but there are several different types of machine integer. Floating point numbers, float and double, and char for characters, which is actually also an integral type. Here are some of the main commands that we use. The if command. Notice that we have to have the round brackets here. These are really part of the syntax. So it's if, we then put a condition inside round brackets, and then the then part we would normally put inside curly brackets. In C and C++, we can read the curly brackets as essentially begin of a block of commands and end of a block of commands. And then with if, there's also an optional else and other commands to do if the condition is not true. Notice that the keyword then here is implicit. We don't write a then here. This is also quite different from what we do in CoCoA5. Here I'm showing two types of for loop. This first one is, let's say, the classical sort, where we have an integer counter, usually starting low and then going up while some condition is satisfied, and this is the increment we do. The classical for loop is much more flexible than what I'm presenting here. And then the loop body, the commands in loop body we put afterwards, again, I recommend using curly brackets. They're not always necessary if this is a single command, but it's probably a good idea to put the curly brackets in anyway. So this is a classical sort of for loop. A more recently introduced one is this sort of for loop. Again, there are several variants. I've shown just one here. So V represents what's known as a container in C++. So it'll typically be what C++ calls a vector, but it could also be a list or some other structure. And then this loop here simply says that X is going to run through the elements of the vector V, and for each element in V we will execute the loop body here. Another sort of loop is a while loop. Once again, we see that the condition is placed inside curly brackets. These are necessary. It's a good idea to put the body inside, in round brackets here, and then put the body inside curly brackets. Other useful things, I think they're useful, are continue and break. We can use those inside a loop body. So continue says go straight to the next iteration. Break simply leaves the loop earlier than we might otherwise have done. So before we've reached the end. And return is for use inside functions to say the return value. We've seen that before. So those are the basic points of the C++ language as such. As I said, there's a bit more I've not explained here. Of course, we can define new user-defined functions here using these. I haven't given the syntax for defining functions. We'll see that when we actually do some practice. The second part of C++ is this standard template library, sometimes just called standard library. It's quite large, so it contains many basic functions, ones that we're familiar with, like square root and logarithm. It's very large, and it continues to evolve as the language evolves. Once you've learned a bit of C++, I really strongly recommend books by Scott Myers. They've got titles like Effective Modern C++ and so on. I like the way they're written. I find they're full of very useful hints and tips. For drier but accurate information, I would suggest, say, the CPP reference website. There's also C++. I think I've heard that that's not quite as accurate sometimes as CPP reference. An old book by Nikolai Yosutis. If you like to use a book, that's also a good thing to look at. Before these websites appeared, this book was more or less essential to anyone wanting to use C++. If you want to look online for help, then one place to look at is Stack Overflow. But as always with such things, be quite careful using this. There are some useful and valuable things in Stack Overflow, but there's an awful lot more junk there. The STL also introduces many extended types. Some that I found particularly useful are std vector. So anything that comes from the STL has this std prefix on the front. We don't actually need to write it when we use vectors, but it is actually there as part of the name. So vectors, so these are essentially arrays with indices going from 0 up to n-1, assuming it's an array with n slots. So the important thing here is that the indices start from 0. There's a class for strings called string. Input and output are normally done via cin and cout. Most of the time with programs using CoCoALib, I've not really used cin much at all. And cout is good for printing. The STL offers things called iterators. I think we'll understand better what they are when we see them, but essentially a way of it's a marker going through the elements inside a container. Also, they have many common algorithms and things like smart pointers and so on, so they're quite helpful. Common algorithms could be things for sorting, even things like getting the maximum or the minimum of two values. They're actually available as common algorithms. So let's have a quick look, see some hints about how we can use C++ ourselves to write our own code. So if you're writing a function, then normally the function will receive some parameters, values upon which it will operate, and will then return a value. And we have two options in C++. We can pass by a value, or we can pass by reference. Now, if we have a read-only parameter, so one we're not planning to change the value of, the two options to consider are either pass by value. This then makes a copy of the value when the function is called, or passed by const reference, which doesn't make a copy. So the second one is appropriate if the value that's being passed in may be a large data structure. If we're certain that it's always going to be small, then we can pass by value. So pass by value is appropriate for built-in types such as integers and floating point numbers or booleans. If we want to have a write-only or a read-write parameter, then we have to pass by reference, a non-const reference in this case. There's essentially no real choice here. You may have heard of pointers. In C++, we almost never need to use pointers. References have largely replaced them, and they're safer. So here are just some examples taken from CoCoALib. I've extracted them from the files just so we can look at them. So the first two, we actually see that we have two functions with the same name. This is known as overloading. So there's a function called isPrime, which can take a long n. So a long is a type of machine integer. It offers typically a wider range than the normal int. And this is the one that I recommend using with CoCoALib. And n is simply going to be the name of the parameter when we write the definition of the function. And its return type is going to be a boolean. So we'll see that we have a very economical syntax here. There's no keyword define or anything like that. We have the return type, the name of the function, and then the formal parameters in round brackets. And the formal parameters, each one accompanied by the corresponding type. This we have essentially the same thing here. The main difference is that it now accepts a big integer. Now, a big integer could be quite a large structure. It may have hundreds or even thousands of digits, so it could be quite large, and we don't really want to copy it unless we have to. So in this case, we use a const reference. So the ampersand here means that we take a reference to the value. We're not going to copy it, and const simply says that we're not allowed to change to change the value, at least not through this const reference here. And once again, the return type is a boolean, which is what we'd expect. We expect isPrime to return a boolean. Another one that's slightly different is quorem, a function that calculates both quotient and remainder for two integers. Now in this case I've just given the simple version using machine integers. Now since we want to have two parameters where we're going to return the answer, the quotient and the remainder, so these need to be, these are in fact write-only parameters. Doesn't matter what values these have beforehand, they never get consulted, but the answer will be put into these two here. So we have non-constant references here. So again, the ampersand corresponds to reference, and since we didn't use the keyword const, then by default it's not const. So absence of the const keyword means non-const in both cases. So that allows us to modify the values in both Q and R. The void here is simply telling the compiler that this function doesn't actually return a value anywhere. So it returns nothing. Next topic, just a very quick recap of something called object-oriented programming. You may have heard of it, maybe you've done some. It's not actually especially difficult. I guess maybe at the start, while people were still trying to understand exactly what it meant, it was a bit fearsome, but not anymore. So it's really a set of guidelines for sort of clean, safe programming. So an object is a value belonging to something called a class in C++. We might think of it in our own minds as a type. And so the value typically, it could comprise no data members, but it's more likely to have one or more data members that represent the value of the type. And normally these would be what are called private. So not many functions or procedures can actually get direct access to the data members. We also have to have something to tell us how we can construct a valid such object. There may be several of these. There may be several different ways we can construct them. A destructor simply says we know is what a function that's called when we no longer need the value, and it destroys the object. In many cases that may not need to do anything, but if the object, for example, allocated some memory, then the destructor would then free the memory that was allocated for it. so it cleans up afterwards. We can have accessor functions, sometimes known as setter and getters. These allow us to have controlled access to the data members in there, so that essentially at every point in the program, the object has a sane value. We can also define in C++ something called member functions and friend functions. So these have the special privilege that they got direct access to the data members. They don't need to go through setters and getters. Advantage of doing this is that we know that the only functions that can actually change the data members in an object are member functions or friend functions, because they're the only ones who have direct access. Non-friend functions and non-friend, non-member functions, they have no direct access to the data members, and so can't change those values. Typically, they can't even read them. We need to use an accessor function so that we can read the value. Something else I'll mention again very briefly, it's a relationship really between two or more classes, and it allows us to share some common structure and possibly some common implementation. Something you could try doing to see an example of this is there's a relatively simple class called small prime in the file numtheory-prime.h. That you would find inside the CoCoALib sources in the directory include CoCoA, and then numtheory-prime.h, and then you look for small prime. A rather longer and slightly trickier example is x in the examples directory x c++ class.c. This will take some time to look through. While it's long, I don't think it's especially difficult. But you may want to look at small prime first, which I think is simpler to deal with. Some more advanced features of C++, which we use inside CoCoALib, but you don't really need to understand, at least when you're first using CoCoALib. If you want to contribute, then possibly you should understand these a bit better. So I've mentioned a bit already exceptions. They're an alternative way of leaving a function, typically used to report errors, and an exception typically cascades upwards. So if a function emits an exception, then typically, and that was called by some other function, then that will continue to keep emitting the same exception up to going up through the call stack until eventually it gets caught by an exception handler. Or if that doesn't happen at all, it gets to the top and then the system does something with it. It may simply just say an exception came all the way to the top, something went wrong, and the program stops. Class inheritance, as I mentioned before, and virtual functions, they're closely related. They're one way that C++ uses to implement polymorphism. Something I won't be saying too much about, template classes and functions. CoCoALib doesn't use those so much, largely because inheritance allows us to achieve most of what we want to achieve. So these are used inside CoCoALib, but at least your first attempts to use CoCoALib can be done really without understanding much about what these are. A few more explicit hints about programming with CoCoALib. So we have types big int and big rat. These represent integers and rationals without any size limit, other than the amount of memory in your computer. We have a type ring, which that's used for representing various commutative rings that CoCoA can calculate with. So a ring could be just a basic, could be a ring, it could be a field, it could be a polynomial ring. So this is meant to be quite a general concept. So it covers all of those. And a ring LM is simply an element of a particular ring. So we've got a ring LM, it knows which ring it belongs to and it knows its own value. So this would typically be representing a polynomial or maybe a coefficient of a polynomial. It's more flexible than that, but these are typical uses. Here are some basic rings. So ring ZZ and ring QQ. These are actually functions with no arguments, so we have to put the brackets after them. And these two rings are essentially created automatically right at the start when we start using CoCoALib. We can create new rings ourselves, so there's new ZZ mod. So if p is a prime, it creates a finite field, otherwise it creates the integers modulo whatever number we've given here. There's a function called new polyring for creating a new polynomial ring. We specify the coefficients, and then typically we would specify the indeterminates this way using a function called symbols. CoCoALib documentation is not quite as nice as the documentation for CoCoA5, although it's fairly complete. Possibly the best thing to do is actually to look through some of the example programs. So that's in the examples directory, and they all have names of the form x minus, and then a vaguely descriptive string here, and then .c. So we have to have .C because that means that this file contains C++ source code. A strangely useful example is xempty.c. This is a program that does practically nothing. And we'll see in just a moment why that's so useful. There are HTML versions of the manual pages, so if you've installed Cocoa, it's probably here. Otherwise, this part here corresponds to the Cocoa root. You then go into the directory doc.html and index.html will get you to a starting point for the CoCoALib documentation in HTML format. But the example programs are possibly an easier way to get going. If you have a look at those. So, writing and compiling. So, an easy way to start writing your program is actually to take a copy of xempty.c. That's the best one. You could take another example if you want, and then you edit it. If you look inside xempty.c, it should also be fairly obvious where it is you're supposed to edit it. You would then save that in a file with a different name. So you don't want to save it on top of xempty.c. You save it in a file with a different name, always ending with the .c suffix. And if you put that in the same directory of examples, you can use the make file that's there, and that then makes it quite easy to do compilation. If instead you've actually installed Cocoa, you'd find the make file at an address a bit like this. I think I'll skip this. If you don't want to copy xempty.c, you have to do some more things by hand. I really recommend that you take a copy of xempty.c. It makes life much easier. So here are some exercises for you to do as well. There are quite a lot of example programs there. Perhaps the first ones to look at would be xbigint1.c, xring1.c. Well, these ones listed here. I don't need to read out the names. Concentrate perhaps on these four to begin with. I think already this one here is starting to get a bit longer, and it may take you some time to understand them. You can also look at, there are quite a lot of examples of xC++, followed by some description here, .c. And this is trying to remind you about certain aspects of the C++ language, so you can actually see concrete examples. So the examples are designed to be looked at, so you should read them and understand them. Then, of course, you can compile them and run them. We'll find out how to do that tomorrow. Another exercise for you is I've uploaded a file with this name here, so it's more or less like the Fibonacci example we saw pretty much at the start of this course. But it's not complete. You have to complete it yourself, and you try compiling it. You probably have to make some more changes until the compiler doesn't complain anymore. Once it's done that, then you can try running it. So I think that's all for now. Hope this gives us plenty of time to do some practical examples.